Okay, Ji. Let's start with a new topic, and that topic is optimal binary search trees. So, before starting this topic, first I want to give you an idea where you can apply these type of optimal binary search trees. So, if you have a translation problem from English to Urdu, maybe, then the vocabulary of English language you can place uh, in an array that is called keys, you can say, and then you can count the probability of English vocabulary through different texts which are available or available text. You can count the probabilities of different words, and then you can place the probabilities of those English words, unique words. That's why I'm calling it vocabulary. So you can place the probability in another array that is called frequency. And there are some issues regarding some words are more probable, and some words are not comes too often, and some may be are absent from the text, you can say. But I'm not going to discuss those issues. I want to remain simple, and I want to remain in a I want to explain the things in a very simpler way so that you can understand. So you can place the vocabulary of English in an array keys and the probabilities of those words in another array frequency. And now if you for example, if you want to translate these English word into Urdu, then the equivalent English words translation into Urdu, you can place the words of those Urdu words in some other equivalent arrays, but those are not concerned here. But you can place. And once you give some sentence as an input to your algorithm, then your algorithm must have some vocabulary. And then you have to search the words in your keys, and you have to search the optimal binary search tree. Every word can come along with different words. So this is something syntactic structure. So for example, if I have a simple sentence, this is a book, then from the simple vocabulary, you may have different trees for this is a book. Maybe, for example, book is the root, and then this is on the left hand side and is on the right hand side, and down to is there is another word, but this is a book, maybe that is a. So what I want to say that if you have this is a book, four words in a sentence, then these four words can form different binary trees or different trees. And as you have to calculate the probabilities, then these different trees will have different total or cumulative probabilities. And but you have to find a tree which will have the small amount of searches, or the small amount of you can say the probability as compared to other trees. For example, one tree has the probability something like uh, zero point 0.7, other has zero point 0.5, and other has zero point 0.9. So according to this probability values, which one has the smallest one? 0.5. So your algorithm must have to give you that smallest probability binary search tree. So this is the application of this optimal binary search tree. But you can apply this problem in various ways according to your use. So let's start properly this topic. And here on the left hand side, you can see I can select first the pen color uh, so that it would be easy for me. So on the left hand side, you are seeing basically according to the lecture that, okay, we have one array that is called keys. We should have one array that is called keys, and there is a condition on this array that it must be sorted. And this key, I can call it, it will contain some values for the keys. And according to this lecture's term, now I am calling it a keys arrays. I am not explaining my these terms into application area. I am just giving you or explaining these terms according to the algorithm. So keys in an array which will contain some keys, and these keys can be English words according to my example. Anyhow, leave it. And another array that would be frequency, and the range is from 0 to n minus 1. It is again up to your use, and that will contain frequencies. Frequencies are probability values. It's the same thing. And what we have to find, and here it is explained that frequency is what? Frequency is the number of searches to keys. I will explain next in this example, but for that time, just be patient. So frequency is what? Frequency is an array that will contain the some value. That value would be the probability value, and that probability value would be the value of some respective or related key, which would be in this array key 0 to n minus 1. And what is our objective for this problem? So objective is that we have to construct we have to find, or we have to construct a binary search tree. This is our objective. We have to find a binary search tree. Actually, according to these keys, we would have different search trees. And from those search trees, we have to find a binary search tree of all keys here. So we have to find a binary search tree containing all keys, and that search tree will have the cost which would be the smallest from other search trees, would be the smallest from other search trees. So what is our objective again? So we will draw all possible search trees, and then from among all possible search trees, we would have to find a binary search tree that will have the lowest cost. And to fulfill that purpose, what would be the input? Input would be an array with keys, and another array with frequencies, and those frequencies would be the probability values of these keys arrays. So this is the definition actually. So now move on. So here we have an example. Here we have an example to understand the concepts lying in this topic, binary search trees. So here we have, for example, we have this array keys, which have two keys actually, 10 and 12, and we have another array frequency that will have the probability. Okay, just assume it that it is probability values. It is not probability values according, for example, it is not fractional value or whatever, but assume it that it is probability value. So, or you can say it is a frequency. So if these are the keys 10 and 12, And if this is another array that will contain the frequency values, and this 34 is the value for 10, and this 50 is the probability or frequency value for the 12. And what are the possible keys? Only partially it is shown. Maybe some other search trees are also possible, but it is an example, so only two sub trees are given. So we can draw a tree with 10 and 12 on the right hand side, and then 12 and 10 on the right hand side, or maybe 10 with 12 on the left hand side, but that is something equal thing, so that's why there is no need to. We can draw, but then the cost of this tree and that tree would be the same, so that's why. Anyhow, leave it. So before going on further, let's try to understand the definition of the cost actually, because I am using this word cost of a BST that we have to calculate in the algorithm. So it is very essential to understand the concept of this cost, and the concept of this cost is mentioned here. Cost of a BST, cost of a BST one node. For example, this is one node. So cost of a BST node is level of that node multiplied by its frequency. For example, this is a node 10, and what is the level? Its level for them here is maybe 1. According to this, we are assuming that the root is at level 1. By default, in data structures, we read this thing that the root is at level 0. So, okay, you can also take it 0, but for example, here, for understanding, we are taking it as 1 to make the thing simple. So, for example, the root level is 1. So, here, this is the node. So, and it is, so we are saying that the level of the root is 1. Okay, that's good. So cost of BST node is what? Is level of that node. So level is 1 multiplied by its frequency, multiplied by its frequency. So this node is 10. Okay, this 10, what is its frequency? 34. So level is 1. So we can multiply 1 with 34, and then we will have the cost for this node. So 34 multiplied by 1, that is 34. So 34 is the node, is the cost for this thing. And here it is 12. So the level is 2. So 2 multiplied by this 50. So that would be 100. So 100 would be the cost of this node. And same is the case here. Now we can go on, because now you will have that concept. So these are the possible BESTs, okay? And the frequency of searches of 10 and 12. If we want to search this key or the word, or this key or the word, the frequency of searches of 10 and 12 are, we know according to this is the frequency of this 34 is the frequency of 10, and this 50 is the frequency of 12 according to the given order. So the cost of the tree, this tree first, this is the first tree. The cost of the first tree is, you can simply say 34 multiplied by 1 plus 50 multiplied by 2. This is level 2 actually. And then you will have the 134 for this tree. And similarly, 50, which is the cost of 12, 50 multiplied, but now it is at level 1. So we are now going to multiply it with 1. So 50 multiplied by 1 plus 34 multiplied by 2. So we have 118. So among these two trees, this tree has the lowest cost. And this is our objective in this problem of optimal binary search trees. So we have to do something like this actually, or you can say our algorithm will compute the cost of different trees, and then it will return a tree with the minimum cost actually. For example, here tree 2 is optimal. uh, Tree 2 is optimal binary search tree among all these things. Now we can move on further. Okay, this is an example too. You can simply, so now I am Doing what? I am enriching the problem. I am, for example, first I will have only two trees, but here now I have extended the example to three keys and three frequencies. And this is not the all possible trees, but only partially displayed some things. You don't have to worry. Your algorithm will compute all the possible trees by itself. So anyhow, so if these are the possible trees, 10, 12, 30, or 12, 10, either 10 on the left side, 20 on the right hand side, this is tree 2, this is tree 3, 4, and 5. You can see different designs of the trees, which are the following possible. So these are the following possible BSTs. So, and it was, you can compute the cost of each tree, but it was seen after computation that this tree, which is the fifth tree, so 20, which is at level 1, so 20, so this is 20, and what is the probability? 50. So 50 multiplied by 1. So here I can see 50 multiplied by 1, and then you have to add all the nodes cost actually individually, and then 10 is at here at level in keys, and it's probability 34, but here at level 2, so 34 multiplied by 2, you can see this thing here. And then 12 is here, and the probability it's 8. So but it is at level 3, you can say. So 8 multiplied by 3, you can see this thing here, and after summing up we have the value 142. The other trees has greater value as compared to this 142, so that's why it's just an example to give you the understanding, so that 142 is now the binary search tree that has the lowest cost among all. So now move on further. We want to extend our concept towards our algorithm. So in a different way. So now this slide will provide you a different direction towards your final algorithm that we will have to run actually. So here you are seeing that what we have understand up to this slide actually, we understand that we will have some sorted array of keys, and that would be from k1 to kn. So now we are talking in general terms, and then we would have another array of probabilities, and that would be from p1 to pn, like that. So what would be the what would be our objective? Our objective is to find a tree that will have lowest expected cost, or lowest cost. This is something that we have seen in these previous slides. Okay, so up to this point that is fine, and we have seen what is cost. We have seen the definition of cost somewhere, maybe here, and that would be the level multiplied by its frequency. Oh, that's fine, that's fine. And here we are saying these things again in terms of mathematical notations, because we have to uh, discuss the optimal substructure property of this algorithm, and then we have to discuss the overlapping substructure property of this algorithm. So that's why we can discuss these things in mathematical notations. So that's why now we are moving towards, basically, towards mathematical notations, and now we are concluding our we are reshaping our discussion towards mathematical notation that we have here shortly. So, so the definition of, for the computation of cost, is something we know that it is something level multiplied by its frequency. Okay, that's good. Now here we will have a little bit different definition for the cost. Cost of searching for a node I, single node I, or any node I, whatever you want to say, that's up to you. So if I want to write these theoretical sentence into a notational sentence, then it would be cost into ki. Okay, that's fine. So any key k any ith key, and we are going to compute its cost, it would be the depth of that ki, the depth of that node, depth plus 1. Here plus 1 is basically something, if you consider the level of the root with 1, then there is no need to add this 1 here in the equation. But if you are considering your root at level 0, then this is something that you must have to add. So this, so what I want to say, so this equation, so this basically this equation and uh, and this definition that you have studied here, it's the same thing, is the same thing. Here we are taking level of the root as 1, so there is no need to add plus 1 here. But here we are going to consider the depth, and in data structures and in existing literature, most of the time we normally take the level of the root as 0. So okay, if that is 0, then you have to find the depth of that node, and then you have to add 1. For example, here, so if I am considering this node and root is 0, so then it is 0 0, and then it is 1, and then it is 2. So 2 plus 1 3. So then it would be, it's something that you can multiply with the 3. You can multiply this 3 with the probability value. So that is I want to say actually. So now, okay, after getting understanding of this thing, so this equation is for one node or ith node in the tree. Now, how can we compute the total cost, total expected cost of the tree? So what is our procedure? Previously, we were adding nodes, 1 multiplied by 50 plus then another node, then another node. So same is the procedure here. So we would have to sum up all the costs of the nodes. So this is from I is equal to n, sum cost ki. So this is ki, I, you can change the value of I, and then you have to multiply the probability value of that node with it. And what is that one? This is the same thing here. This is the same thing. So the equation is quite clear, and then you have to add up all these things. So that's why it's a sigma, and from I is equal to 1. Okay, that's fine. And in the next step, you can change this cost into I. This is the formula that you have seen here. You can replace this value here with this one, cost into ki, and then you can replace this value here. So depth into ki plus 1, and then pi, very simple. And then after that you can multiply it. Pi is multiplied here, pi is multiplied with 1, I will have the pi, and then you can apply the sigma separately. Okay, then this is something that you will get. And after that you are taking common again the sigma, depth, ki, pi, and then plus 1. So it is something, what it is the depth of the node plus the probability of all the nodes, and multiplying depth with probability, and okay, that's fine, and then summing it up, and finally you have to add this one. So this is something. Now finally the formula for the calculation of the expected cost of the tree. um, and now we have seen, or now we have closed our previous whole discussion from slide 1 to here in a mathematical equation, this one. Now if this equation, expected cost of tree is equal to sigma is equal to 1 to n, depth into ki, pi, and plus 1, if this equation will come in front of your eyes, now you will understand that what this equation means. And that is the objective of all the previous slides, and here this slide actually particularly. So let's move on to apply if we want to apply these concepts, now again with an example, then let's see these concepts. I am basically trying to give you different examples existing in different literature so that uh, your mind will not scattered, and you will be able to get the concepts lying behind this optimal binary search trees actually. So here, um, if I have this I 1 2 3 4 5, okay, that's fine. If these are the keys K1, K2, K3, K4, and K5, and these are their probabilities, and if I have these two trees, different trees, this is K2 as a root, and then K1, K4, K3, K5, and I have mentioned these probabilities according to this table. For example, K2 has the probability what? This one. K1 has the probability what? This one. And K3 has the probability what? This one. So in this diagram, you will find these things in the same way. Can I erase all these things? Yes. Erase pen, yes. That's good. Okay, same is the case here. So I have these two trees. And now I am going to calculate the cost of these trees uh, without any algorithm. But I have the concept in my mind. So this is given and it should be sorted. So that's why, according to our algorithm, this would be sorted. So we can sort our keys, which are given here. Here it is not sorted, but you can sort it. And after sorting, it would be like this: K1 less than K2 less than K3, or like that. And then you can place all these keys in your array. And the first tree, the tree one, the first tree, which is this one, this is our first tree. And the first tree is K2 is the root, which is here. This is K2. And then to represent its children, we are going to use the division symbol actually, this one, division symbol, in the next slide. So K2 and then divided into what? Into K1 and K4 according to this one. This is K1 and this is K4. Okay. And then this K1 and K4 is further divided into what? K1 has no any children. It is a binary tree, so it should contain at least two children, but there is nothing here. So that's why we have mentioned in scale brackets nil for first children and then second children, which is nil actually. So these are the entries for K1. These are the entries. These are the entries for K1. Okay. And then K4 has what? Okay, then comma, and then K4 has what? I am also considering the children, but I am also considering the level or the depth actually. So K4 has K3 and K5. That's okay. So K3 has K3 here, comma K3 and K5. So this is also a representation of that tree into this format. And now you can multiply their cost. So root has the depth 0. Root has the depth 0, which is mentioned here. And I have to multiply this depth with its probability. And the probability of the K2 is 0.20 are here. So I have to multiply here with 0.20, then plus, and here K1, K2. So I have to add these. So what is the probability of K1? Probability of K1 is 0.25 and the probability of K4 is 0.20, which is mentioned here. You are adding and then you are multiplying it with the depth. Depth is 1. Depth is, this is the depth actually. This is 0 and this is 1. This is 2. Okay. And then same is, now you are going to, okay, this is nil, so nil is nil. you will get nothing. So the simple is you can just ignore them, and then you can move on, or you can calculate them and then you will get zero. And here, and after summation, it will be totally avoided, or it will be totally removed from the calculation actually. So K3 and K5. So K3, sorry, K3 is point 0.5 and what is that? K5 is 0.30. Yes. So 0.5 and 0.3, you can sum it up, multiply it with 2. And so, so after multiplying with probabilities and adding up according to this one, we have multiplied keys with the probabilities, and after adding up, now you are going to add plus 1. So now this is that plus 1. And after calculation, you will have the values like that one, 1.15 plus 1, which is basically 2.15. And same is for tree 2, you can do it by yourself. And then 1.0 plus 1, that would be 2.10. So this would be 2.10, this would be 2.15. So this would be something, the second tree 2 would be the optimal binary search tree with the expected lowest cost, as mentioned here, the deeper tree. This one, this tree would be optimal tree. This will give us smallest values. So this is also another example to understand this BST from a different sources. So you can also see this problem at various locations in a different, with different explanations, but the concept is same, what I want to say there. So now move on. Now we can move towards our dynamic, because we are basically considering, we are basically are mainly considering the dynamic programming, and this optimal binary search tree is also a problem in this domain of DP. So now we are going to see that either this problem has this optimal substructure property, and then we will see that either this problem has the overlapping substructure property. So we will have to discuss these things shortly. So optimal substructure property. According to our previous knowledge, optimal substructure is something in which we will have to divide our problems into subproblems, and then we will have to solve, and then we will have to solve. Okay, so so in optimal substructure, we will see that the problem has some subproblems, and the solutions of those subproblems uh, you can calculate through some recursive approach. Uh, in other words, during finding the optimal substructure property, we will have to search that the problem has some recurrence or not, or recurrence relation has not. So if the problem has some recurrence relation, in this is something I am talking according to the mathematical notations, actually. So we have to find some recurrence relation. So this equation which is displayed here in front of you is basically that recurrence relation, um, which is explaining something, which is also this equation is giving you the concept that you will have to calculate this thing in this way, and also by using recursion. If your equation, and here for example, how can we compute the optimal cost from node I to node j, and node I, maybe it's the root node, and j is maybe the final or the last node, leaf node of that tree. So So this is something, if a tree has nodes from I to j in total, then how can we compute the optimal cost for that tree from node I to node j? So this is something that we have to find. So the solution is given on the right hand side. The recurrence relation is given on the right hand side. The first part is giving you this information that you have to sum up all the frequencies of the keys, all the, so for example, if I have 10 keys, then I will have surely 10 probability values in my frequency array. So what I want to say, that I have to add all frequencies. This is something given here. And then I have to sum up these frequencies with another minimum thing. And what is that minimum thing? This second portion is giving you the concept, but it is optimal cost. This is optimal, and this is something recursion. So this is an equation that you can use in your algorithm or in your program to calculate something recursively. And this is saying that you can calculate, you can divide your problem, which is from I to j, which has nodes from I to j. You can divide your problem from node I to r minus 1, and then you can compute from r plus 1 node to j, and something is left in between. This is from I to r minus 1, and then maybe r somewhere, and then it is r plus 1 into j. So this r is left, and this r we will use as a root of this tree, or you can say this is one subtree and this is another subtree of this root node r, which is not mentioned here. We can handle this r in our algorithm or in our program actually. So, and in this way, when I will call my algorithm and I will call this statement somewhere in my algorithm, then this will compute the optimal cost of the left subtree, which would be from I to r minus 1, and then the optimal cost from the r plus 1 to j, which would be the right subtree of that r, and this cumulatively would be, and then, and for example, when you will have this, when you will call this optimal cost from I to r minus 1, again you will call this thing, and now your I is I, but your j is now changed, it is r minus 1. Now your j is changed, and then in this domain you will call this equation again with with further divisions, and in this way, with further divisions and divisions and division, maybe you will finally reach at some leaf node, and then you will get the frequency of that leaf node finally. So it means that if your program is recursive, then maybe you have some base case, and this is your base case when you will finally come up with final leaf node, and then you will return the depth, and then you will multiply the frequency and something, and in this way, in backing upward direction, you will have your values finally for this root node r. So this is something recursive equation. So in the first portion, what you have to do, you have to add sum of frequencies from I to j. This is the first part. And in the second part, you have to try one by one, try all nodes as root. So as we know that in our problem, we have to compute all possible binary trees, and then we have to find that which binary search tree has the lowest cost. So it means that then we have to change are keys one by one um, for each subtree at the root level. So if I have three keys k1, k2 and k3, so in one tree k1 will be the root node, in another tree k2 will be the root node, and in another tree k3 will be the root node. And in this way I have to calculate all these trees, and I have to calculate these things recursively according to this equation, which is a recurrence relation for any root r, and from I to r minus 1 and r plus 1 to j as mentioned here will give you your required result. And finally your result will be at this position, optimal cost 0 and minus 1. For example, if you have two-dimensional array, or if you have a table in two-dimensional rows and columns, then 0 and minus 1 will be the position that will give you your result, or that will give you your optimal value for the binary search tree. Okay, moving on. This is the program which you can type, and you can see the result. And here, this is the portion where this recursive equation is used. So you can say, okay, let's have a look. So anyhow, optimal cost frequency I r minus 1 plus optimal cost frequency r plus 1 into j, sorry. Um, so this is the right hand side, are the second portion of this recurrence relation here in this source code. And here we are summing up frequencies by calling some other function, which is that function, actually, that function where we are multiplying these frequencies. Let's have a quick look over this program, because actually we will calculate these things according to my previous practice in a very much detail here. Here I will run this algorithm properly by calculating some values. So the detail will be at this, we will see the details at this slides. But before that, this is something for your exercise actually, because it's an algorithm, it's a um, proper source code written in C language, that you can C programming language, that you can type and you can see your results. So this is the main program. I have this array of keys 10, 12, 20. Frequency array is also given. And okay, size of keys divided by size of keys. Size of keys is 3 divided by size of key 0, which is 1. So 3 divided by 1. So 3 will be returned here at n. Cost of optimal BST percentage D, optimal search tree with keys. So keys is that array that will go as an argument here. And then the frequency is another array that will go as an argument here. And then this n. And then this n, which is 3 for this example actually. So now we are calling which function? Optimal search trees. Okay, so this is our optimal search tree, this one. And this optimal search tree with keys, frequency and n, and this function is containing only single statement, return with optimal cost, and then frequency is the frequency array as it is, and then 0 is the starting point, or you can say I will use this for the root node actually, and then n minus 1, this n, and then n minus 1. We are going to start it with 0 according to conventional things, and so that's why. And if it is starting with 0, then n minus 1. And now this is the optimal cost function actually. Here the frequency array int ij, And now this is the base case. According to our previous discussion, what would be the base case? The base case, there are two base cases here. One is when you are left with only single leaf node, and then you have to calculate the value or the probability of that uh, that sorry then you will have to calculate the cost of that single node actually. So that is your base case. And this is another case in which you can say uh, when you don't have anything left after calling the function again and again and again and again, calling this function again and again, and finally at the last step you don't have any node left. So that is the case actually if there are no elements in this subarray. So anyhow, so this is the starting node location you can say, and this is the mm, ending node location for this call, and here it is 0 and minus 1. So n, if n is 3, then it is 0 to 2, 0 to 2. And here you can see that 2 is less than 0, 2 is not less than 0. So condition is false, so it will not execute. I will come here. And 2 equal to 0, no, this is false again. So I will come here. And here it is sum frac 0 and 2 will go as an argument, and I am calling this function sum actually, which is given here, sum. So frac is the frequency, and then 0 and 2, s is 0, and then k is equal to I, which is 0, and 0 less than or equal to 2. So 0, 1, 2. So it will execute 3 times, and it will sum up all the frequencies which are lying here. It will sum up all these frequencies, and it will keep these sum in S, and then returning that S, okay, and that S will come here. Maybe that would be what would be that value? So 50, 34, 84, and then 92. So 92 would be the sum actually. So 92 will come here as an FSM. And after that, we have another variable min, and we are initializing that variable with infinity, integer maximum integer according to that programming language. So you can call it positive infinity. So min has some value that is positive infinity. And after that, we have a loop for the root node actually. So one by one, consider all elements as root. Now you are going to consider all these elements one by one. These elements, you are going to consider all these elements one by one as a root. This is the loop which is going to do that. One by one, consider all elements as root and recursively find cost of the BST. And each time, for example, now I have this call to this I have the call to this function with 0 and 2, value of j is 2 actually. And okay, so now r is equal to I, which is 0, and 0 less than or equal to 2, okay, true, plus plus, so it will execute how many times? 0, 1, and 2. So it will execute 3 times. And then here, optimal cost, you are calling function optimal frac, which is a frequency table or frequency array. I is 0 and R is initially 0. So 0 minus 1, minus 1. So 0 minus 1 is what? Minus 1. So from 0 to minus 1, you will call it. Okay, call it. Call this function. And this will be from where? 0 plus 1, 1 and 2. This would be first call. This would be for 1 and 2. Sorry, this is really an issue. in online programming language when you don't have the resources. Okay, this call would be initial call for 1 and 2. This is the I r plus 1 value and this is the jth value, and this would be for 0 and 0 minus 1 minus 1. Okay, call this optimal function again. It would be 0 and it would be minus 1. The value of j is minus 1. Here you will check minus 1 less than 0. Yes, return 0. So this function will give you the 0 value. Here, this function will give you the 0 value. And in this way, it is terminating actually. But, and here, call this function again. You have 0 here. Call this function again with 1 and 2. Okay, 1 and 2. Ith value is 1, jth value is 2. Okay. 2 less than 1? No, false. 2 equal to 1? No. I will come here. You will again sum up the, you you are calling this function, you are summing up some values, and then you are going to execute this loop again. And this recursive equation will be called again. And you have to record all these values. So what this loop is doing, in this way you are getting, maybe when this will be executed and when this will be executed with the base case, or when you will have some value here, 1 or 2 or whatever, I don't know, maybe 34 or whatever, I don't know, then you will have that cost here. And then you will check 34 less than this min is, initially it is positive infinity, which means the largest the largest number than all existing numbers. So 34 is less than min, yes, and then you are finding some minimum, so then you are updating this cost 34 into min. And when you will have all these calculation done, then finally you are adding up this min and the FSM, that what you will have, you are adding and then returning, and when it means that you will have your value here finally. And in this way, the cost of optimal so your algorithm here, this program will calculate different BSTs, and finally with its total cost actually, and finally it will give you a BST with the lowest cost, that is the 142. We will see these things in detail on our small whiteboard, but but the point when I will reach at here maybe, then I will discuss all these things in a very much detail. Okay, so what was the purpose of this source code and its presentation? The presentation of, or the purpose would be that there is some recurrence relation, and this problem is containing the optimal substructure property. And optimal substructure property is a property in which a problem is divided into further subproblems, and you have to recursively solve those subproblems, and then by using the solutions of those subproblems you can finally come up with the solution of the main problem. um, so this is your recurrence relation, and here you are seeing that we have a source code with this. This is your optimal cost, or you can say this sort, the second part of this recurrence relation, and the first part of the recurrence relation is here, which is a call to this function sum, which is given on the next slide, this one. And in this way, this will give you something. Keep this thing in your mind that whenever you will have, I can clear up these things. When you have recursion in your source code, then normally and this loop is running how much time from I to j, which means the total size of the initial BST, it is for example 0 to n minus 1, this loop. So this loop is running n times. And here you have recursion and it is 2 times. So when you have this thing like that, so then it means this 2 is for recursion and this is running n times. So keep this thing in your mind that the complexity of this problem would be exponential when you have recursion. And when you will call this function, we will call this function again and it will again run this loop n times and then again 2 calls. And if I will have 3 calls here, then it would be 3 raised power n, 3 recursive calls. And if it will be 4, then I will have 4 raised power n and so on. So generally, so that's why generally here we are saying the time complexity of this recursive approach is exponential. Now moving on to the second part of the DP problem, and the second part in which we have to look something or in we have to see something is the overlapping subproblems property. What its definition? According to our definition, we overlapping subproblem is a property in which we know that the problem has subproblems, and and these subproblems are overlapping. Repetition. For example, if I will go towards the previous slides, maybe I don't know. Let's have a look. Maybe I have that slide. I don't know. Where is that slide? I don't know. So in which the same subproblem is appearing again and again, and if you are calculating your same subproblem again and again, for for example, in previous lecture I have shown some tree with first call from 1 to 4, and then I have another call 1 1 1 2 1 3 and so on, if some student is reminding. Then we have seen there that 1 2 or maybe 1 1 were calling in again, were appearing again and again in that tree. So that is the appearance of the same subproblem and again and again. And if you have the situation like this, then you have to compute that subproblem again and again, and it will increase the timing of the algorithm, or it will disturb the efficiency of the algorithm. So what is the solution? Solution is that you can store the solution of that same subproblem into some array, and then you can use that result when it will be called again, rather than the computation of that subproblem again. So that is mentioned here. So I'm just reading these points. Since same subproblems are called again, this problem is basically, this is the problem that we can call it overlapping subproblem property. And this problem, BST basically, optimal BST problem, now has both the properties of DP problem, which means that optimal BST has the optimal substructure property, and the optimal BST has the overlapping subproblem property. And if we have the overlapping subproblem situation, then the only thing that we have to do is we will have to use some array or table in which we have to store the solution of that subproblems, which are in repetition. So here it is mentioned, recomputation of same problem can be avoided by constructing a temporary array, and here we will use another array. Key is one array, frequency is second array. Now we will use another array, the third array, name cost, with two dimensions in bottom up manner. So it is very much similar to our previous practice. So some further things about these cost. This cost nn would be an auxiliary array, and we know that we will use it to store the solution of subproblems. And in this array, the index 0 and -1 will finally give us our result. Okay, keep this thing in your mind. This is one point. What it means? It means that, for example, here have many indexes, but this is something 0 and -1, 1, 5. This index, this one will basically contain our result actually. This is something want to explain here. So cos 0 and -1 will contain the final result actually, result of our algorithm, or the optimal value of our algorithm. And then, okay, I'm just explaining that how we can use this array cost nn. So all diagonal values must be filled first. So if we have two-dimensional array, if we have two-dimensional array, then what you have to do, you have to fill all these diagonal values first. Then the values which lie on the line just above the diagonal, then you have to evaluate this line. If we talk these things in notational way, then it would be that we must first fill all cost I values I. For example, this is 1 I, 1 1, 2 2, 3 3, 4 4, and then all cost I into I plus 1 values. This is the next level, and then cost I into I plus 2 level, and so on. You have to calculate the values like this one. And this portion, it is not needed because it is just a repetition. It is just a repetition. So it is a very much similar idea to our matrix chain multiplication that you have seen in previous lecture with quite detail. So let's move on. So this version of the source code is basically the source code without recursion, and it is, you can say, according to the textbook that you are following, or we are following actually. Textbooks is basically for the teacher always. The definition of textbooks is that a book which the teacher is basically following, and students don't have to follow that book. But here the practice is different, so anyhow, no issue. So this source code is according to this approach, according to the textbook approach. If you want to change your source code to recursive approach, then keep this thing in your mind that the complexity of this approach is lesser than the approach with recursion. Recursive approach has exponential complexity, and this non-recursive approach has the polynomial complexity, which means it may be n cube, maybe n square. So it is polynomial. So that's why the best is kept here for you. So Just a quick just a quick run from this code. So the main program is same. Call this optimal search tree. So this is optimal search tree. The keys, frequency, and then n. This is cost and n, that now we are going to store the solution of subproblems in it. And then I have a loop 0 to n. For example, if this is 3, 3, 3, so calling this function with 3, the cost would be 3, 3. And then from 0 to less than 3, so 0, 1, 2. So it would run 3 times actually. And after running 3 times, it would do what? For a single key, cost is equal to the frequency of the key. Yes, I know that. For example, for a single key, the cost is the frequency, this frequency of that key. We know that. So we are basically summing up all the frequencies and we are keeping it in cost in a similar way that you have done here in previous approach with this statement. Okay. Now I have a loop starting with a variable L, and we are starting with 2, and then, okay, I don't know what is this L. So, okay, integer L is declared. We are starting it with 2, and then 2 less than or equal to 3, L plus plus. So it will almost execute n times. And then this loop starting with 0, 0 less than or equal to n. N is 3, L is 2, 3 minus 2, 1 plus 1. So it is maybe 2. So, so, so minus 2 plus 1, minus 2 plus 1. So minus 1. So 3 minus 1. So 2. So it would be 2 initially. Initially it would be 2. So from 0 to 2, 0, 1, and then equal is 2. So it will again run 3 times. And here what you are doing, you are changing the value of j here. Here you are changing the value of j. Here I have the value of I. And here you are keeping, you have the I value and jth value. And now you are keeping the infinity, positive infinity in this cost ij, whatever the value is. And then this is the loop for the root actually. The same, the same, the same loop. And now here you are doing something similar to calculate the cost actually. When I have this r is equal to, maybe initially it is 0. So r is 0, 0 greater than I is 0, 0 greater than I, it would be false. False, it is a conditional statement, and when it is false, it will return this 0. And 0 less than j, j is what? J initially I have to see 0 plus 2 minus 1, 2 minus 1. So 2 minus 1, 1, 1 plus 0. So initially j is, I think, 1. So here r is 0, 0 less than 1. Condition is true. So this, I will check this thing. And that value would, this value 0 plus that value would be summed up. And I will again call the function sum frequency ij, which is this one. And after summing up the values, the s will be returned here, which will be sum up again here. And then I will get the value of c. Here I am checking the c is less than cost ij somewhere. And if it is less, then I am keeping the minimum here. And I am updating the minimum here. So this is something we will see. This is something according to our this approach. Here you can see, we will see. So, but you can type this source code and you can have your output like this. Okay, before continuing the actual topic. So let's have some. Uh, by the way, what is the complexity of it, of this approach? Just a idea. So this loop is running. Okay, we are calling this function. This is a main program. We are calling this function. Okay, and this is a loop, but it is ended. So it is an independent loop which is running n times. This is a loop almost n times. This is another loop almost n times. This is another loop almost n times. So it is, these are nested. So n cube. So n cube is sure. N cube is sure. Plus this n you can say. But this we normally keep plus this n. But we normally keep the higher values and these values are ignored. So n cube is something. N cube. Let's have a look. Sorry. This is sum here. We are calling some function again. We are when you are calling this function again and here this loop is also executing almost n times, and this loop, which means this loop is also nested here. So the complexity of this algorithm is n raised power 4. Okay, and this is polynomial, not exponential. Exponential is when you have 4 constant here and variable here. So this is something exponential, but this is polynomial. Anyhow, now let's have a look over these notes. The time complexity of the DP solution is order of n raised power 4, which can be reduced. So you have seen this, this is n4. So we can reduce it to order of n cube. We can reduce it, okay. But how? By pre-calculating sum of frequencies instead of calling sum again and again. He is saying that the function that you are calling here, sum, you are calling this function again and again with the iteration of this loop. And he is saying that this is not a good approach. You can uh, pre-compute these values and then you can use those values here as it is rather than calling this function again and again. So you can modify this algorithm and then you will have the complexity reduced to n cube. And then uh, another note is in this solution, we have computed optimal cost only, which can be modified to store the structure of the BSTs. So this algorithm is basically giving you the optimal cost of the BST and not the structure of the tree and not the structure of the oh no and not the structure of the tree and not the structure of the tree like this. So this is only giving you the optimal cost. So you can alter, you can modify this program so that it will give you the structure of the tree also. And if you want to do this, you have to introduce another array, auxiliary array of size n to store the structure of the tree. And how you can do that? You can just use the value of r in the innermost loop. In the innermost loop, here you have this value of r. So you can take benefit from this r value and you can use some another array where you can store the value of r and then you can print the value of r again and again, and in this way you can have your tree structure with you. So let's have a small break for me. Okay, I am back now, and now we have to start from here. Uh, Before discussion, let's have a look over these slides and Just a moment, I am searching for my, yes. So now glasses are on and now we can continue. So here two BSTs are given to us with keys and their probability values, you can say, represented with D0, D1, D2, D3, and so on. And keys are from K1, K2 up to K5. This is one BST, this is another BST. So two binary search trees of set n is equal to 5 keys. So Rn is now 5. And we have these probabilities. Pi is represented, if we just make a table for a better understanding, I is 0, 1, 2, 3, 4, 5, and Pi is the probability value, probability value for mentioned here, and Qi is also basically the probability values mentioned here. And it is mentioned that this ABST has finally the optimal uh, BST cost as 2.80, and the other BST has the optimal cost as 2.75 and this slide is giving us an understanding that this BST has the lowest cost. But how this BST has the lowest cost, now we will see these things. So let's move on to the next slide, and I am now cleaning these pen marks. So I'm just stopping my video so that we can have the understanding of the algorithm first. So this is our optimal BST algorithm with P, Q, and N as an argument. What is P? You have seen in previous slide that this is our P, this is our Q array. Now this P, Q, N as an argument, and then we have E. This is your E. E, you have to initialize this E with 1 to n plus 1. N is 5, so 5 plus 1, 6. So 1 to 6 and 0 to 5. Similarly, W is 1 to 6 and 0 to 5. This is W table. And there is another table which contains the information of root. And root is 1 to n, mean 1 to 5, and 1 to 5 be the new table. So these are the tables now we have. And now I will turn on the video so that you can see the things. So this is the table that you are seeing. Is according to the algorithm, I have to draw E from 1 to n plus 1, which is 1 to 6. So this is E 1, 2, 3, 4, 5, 6. And what is the column width? On the site is 0 to n. So 0 to 5, 0, 1, 2, 3, 4, 5. That's fine. So we know that I will put some value, then I will remove half of the portion of this table. Until that time, we are just going with this complete table. And then we will see that which part I have to consider and which part I have to remove. We will see that. And similarly, this is the W. Here it is W with the same initialization 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 5 according to this statement. It is mentioned here. You can see. And then there is a root. So you have to keep the color of this board in your mind. And then this small table is for the root. This is for this is root. And what is then its initialization? It is from 1 to n and 1 to n. 1 2 3 4 5, 1 2 3 4 5. So I will use also this table also. Anyhow, now let's start with the algorithm. So what the algorithm is saying, just have a look over the slides first. Here I am again stopping the video so that you can have the complete focus on the slides. Here for I is equal to 1 to n minus 1, I is 1, n plus 1, 5 plus 1, 6. So this loop will run 6 times. 1, 2, 3, 4, 5, 6. So this loop will run 6 times, and it will do what? It will, so value of I is 1, so 1, and it is I minus 1, 0. So 1, 0, and it will keep the qi. Qi is 1. 1 minus 1, 1 minus 1 is 0. So q0. The value of q0, the value of q0 is this 0.05. So value of q0 is 0.05. So 0.05, it will store that value into 1, 0 at E, 1, 0. So this is 1, this is 0. So this is basically the position where it is storing that value. Anyhow, I am removing these things again. So let's have a look on this board now. This is E. So what is the value of qi? Qi, I is 1. 1 minus 1, 0. So q0. Value of q0 is 0.05. So 0.05, I have to place it here. I is 1. You have to look on the slides and also here. When I will write something here, you have to look here, and then otherwise you have to look on the slides. So E11, E10, 1, 0. So here. So here I have to keep the value. What value? 0.05. 0.05. Hope you are seeing this value, 0.05. Now this one, which is again q0, which is 0.05, you have to keep this value 0.05 where? In weight matrix, and it is 1, 0. So weight matrix is where? This is the weight matrix. This is the weight matrix, and I have to keep this value 0.05 here. Okay. Now the loop will run again. The value of I would be 2. It will run 6 times, as I said. So now the value of I would be 2, and then in E21 you are placing Q1. What is the value of Q1? What is the value of Q1? You can see from here, this is the value of Q1, which is 0.10. So you have to store that value 0.10 where? E21. 2, this is E, this is 2, and this is 1. You have to keep this value 0.01 here. And similarly, you have to keep this value in weight matrix 2, 1, so 0.10 here. And you can compare these values. You can compare this value here and here, and similarly here and here. And now the loop will run for I is equal to 3. And when I is equal to 3, so this q I minus 1 will give you the value of 3 minus 1, 2. So q2, what is the value of q2? You have to look over. This is the value for q2, which is 0.05. So 0.05 value you have to place at 3, 2, 3, 2. So this is weight matrix. Anyhow, you can see. So this is 3, this is 2. You have to place this value 0.05 here. And same is here. Okay. And now you can go on like this and up to 6 times. And what are the value? 0.05 again, 0.05 again, and then 0.10. So you have to keep this because this loop will, so here you have to keep the value 0.05 here, and then 5 4.05 here, and then 0.10 here. Same is for E, 0.05, 0.05, 0.10, like this. So this loop will now ended, and you have the values like this in the diagonal. Okay, when this loop from line 2 to 4 will end, it will initialize your diagonal in the two matrices, like this. Okay, that's fine. Now we have to move towards the next for loops, and which is at line 5. So now I can use this board actually. So I am writing this for, now my L is L is equal to 1 to n. So L is equal to from 1 to n, and 1 to n is 5. L is equal to 1 to 5. Okay, and then there is another loop, for I is equal to 1 to n minus 1, nested inside it, another loop for, and it is I is equal to 1 to I is equal to 1 to n minus L plus 1. N minus L plus 1. And what would be its value? So n is 5, L is 1. So minus 1 plus 1, it will be cancelled, so n is 5. So okay, I can write it, it will run. So this loop will run for 5 times. 1 to 5. Okay, that's fine. This loop is now done. And now the next value under it is the value of j. And the j is here. J is I plus L minus 1. I plus L minus 1. And what was that one? L is 1. 1 minus 1, it is cancelled. And the value of I is 1. So initially, the value of j is 1, you can say. Initially, the value of j is 1. So value of I is 1, value of j is 1. And now I am here at E into ij is equal to infinity. Okay. E into ij. I is 1, j is 1. I is 1. So E11 is infinity. So what I have to do, I have to place infinity E11. So this is 1, This is E 1 and this is 1. So I have to place infinity here. So I am putting dot here for infinity, which means the maximum number is here. Maximum positive number is here. I am I can write infinity actually. Then you have to remove. I can write infinity. So okay, infinity is done now, and then the next statement is saying you have to keep something in W matrix, which is that one. And what you have to keep it here on the right hand side. So W I is 1, J is 1, 1 and 1 is 0. So W10. So take some value from W10. So W10 is this value 0.05. So this value I have to consider. So take zero point 0.5 and then Pj plus Qj. J is 1. So P1 and Q1. Take the value of P1 and Q1. What are those values? I can see from here. These are those values. P1 and Q. These are those values. And after adding it up, it would be 0.25. 0.25 plus this value. What is that value? 0.05. This one. 0.25 plus 5. It is 0.30. So I have to keep 0.30 where Wij. I can I can write it here. So first E I am just writing Eij is equal to infinity, and then I am writing Wij is equal to what? That would come here actually. Wij, that would come where? Maybe it is difficult for you, but I don't have any option actually. So now I have to keep some value here at weight matrix. This is my weight matrix. So by considering Pj and Qj, by considering these values from previous slides, 0.25 and this Wij minus 1 value, which is 10, weight 10, this one, 0.25, which is, so after summing these values up, we have 0.30, which I have to keep at W1 1. This is 1, this is 1. So I have to keep this value at here 30. And you can verify this value from here on the slides I have highlighted. And now it means that I don't need these. Oh, sorry. Yes. I don't need this part. I don't need this part. Or if it is drawn, no issue. So, and then you can see your diagram. I don't need this part. Or I can write my numbers here 1, 2, 3, 4, 5, and 6. And I can also remove these. So this is your diagram actually, which you are seeing on the slide. This is your diagram for weight. And similarly, I will do the same things with other things. So anyhow, I am here. This statement is done now. This statement is done. And this statement has now, I have another loop. I have another loop that is for loop, which is inside this loop, for loop, and it is from r is equal to I. R is equal to I. I is what? 1. So I am writing it 1. R is equal to 1. 2j. 2j. J is what? J is also 1. J is also 1, this value. I am highlighting for your understanding. I need these IGA values because it is too much involved. So from R is equal to 1 to J. So it means that this loop will run one time. This loop will run one time. Okay, that no issue. Now I am coming here at this statement. This statement is saying what? This statement is saying that I have to take some value from here, then I have to add this value to this value, and then I have to add this value to this value, and then I will get some value at in t. After that, I am checking that this t is less than existing value, some value at this position. If it is less, then I have to update that minimum value here in this E matrix, and I have to update this R, which is basically the root, into the root matrix. And this loop will go on. When it will end, I will come here at this loop. When it will end, I will come here at this loop. And when this loop will end, I have to return E and root. Let's see. So E I is 1. My R is also 1 actually. My R is 1 now. So 1 0 E10 E10, what value I have at E10? I have, you can see it from the slides, 1 0. So these red values are something that I have computed on my board also. I am just highlighting. These are the values of the initialization that I have done already. So I am just highlighting that these values I have computed. This value I have computed, and okay, from E1 and 0, what is the value at E10? I can check that value from here. Now from this board. This is E10. This is 1 and this is 0. So value is 0.05. Okay, this value I have highlighted. And then E2 1. Value of R is 1, so it would be 2 1. 2 1. So 2 and then 1. That value would be 0.10. Okay, and then Wij11. W11. So this is my W. This is my W. My 11 is this value. 1 and 1. 1 and 1. My 11 is 30. So 30 plus these two values, 10 and 15, 10 and 15. So 30 plus 15, 45, 0.25, 0.45, sorry. So I have to, so now my T is, so now my T has what value? My T has, my, so now my T has what value? 0.45 after computation. Or, or I can say T E E1, if I have, if I consider these things, E and then wait, then I can say, my E comma R minus 1 value is 0.25 plus E R plus 1 comma J value is 0.10, and then Wij has a value 0.30. So this is something I am computing according to that algorithm. So in this way, I am getting 0.45. In this way, I'm getting 0.45. That is my T. That is my T. So now I am checking on the slides, please. On the slide, please. So now I am checking that if 0.45 less than, if 0.45 less than E11, the value of I and J is 11. So T is what? 45 and E11. This is E. So this is 1 and this is 1. So this value, the value is infinity there. So 0.45 is less than infinity? Yes, of course it is less. And if it is less, and if it is less, then what you have to do, you have to keep this value 0.45 at E11. So I have to update this infinity value with 0.45, which you can verify from the slides at position this one. And then you have to keep the R. What is the value of R? R is 1. You have to keep the value of R into root 1 1. And now you can say this is my root 1 1. So here in this cell I have to keep R 1, which you can verify from here 1 and 1. So this is the value. Okay, that's fine. Okay, now the loop is ended. Now the value of this loop I1, 1 to 1. I know from this algorithm for loop R is equal to 1 to 1. So this loop would have to execute for one time actually. So the loop is ended and I will go back to this loop, and then I have to increase or increment the value of I. So the value of I is, initially it was 1 and now it is 2. Initially it was 1 and now it is 2. The value of I is, I can say, the value of I is now 2. When the value of I is, now you have to compute these things again. So J would be, L is 1. So 1 minus 1, 0. So I. So the value of J would be, again, it would be 2. The value of J would be 2. And then EIJ. E, this is 2. I is 2. I is 2. J is 2. So E22. So E22 would be infinity. So if it is infinity, then I have to 2 I have to update this value here. This is 2 and this is 2. So this is infinity. Okay. And what is the next thing? And then Wij, the next statement on the slides. Wij is equal to W2 and 1. W21, 2, 1. W21 is 2 and 1 is this value, 0.10. And P2, Q2, what are the values for P2 and Q2? These are the values for P2 and Q2, which is, after summing it up, you will have 15.15. So 0.15 plus this value 10, I will have 0.25. 0.25 I have to keep at 2. At this is my weight matrix. So this is 2 and this is 2. Here I have to keep 0.25. Now verify it from here. Yes, it is verified. 0.25. You can see on the slides I am highlighting with red. 0.25. And then the next loop for R is equal to 2 to 2. I and J has the value. I and J has the value. According to I and J has the value. I and J has the value 2. So this loop will run again only for one time. And now you have to compute the values in the formula. Now look over the slides. In the slides, okay, 2, the value of r is now 2, or you can change these values here. This is now from 2 to 2, from 2 to 2. And now you have something, you have to compute something here. So E21 is what? E21, you can take this value from this slide, E21, or we can take this value from here, E21. E2, 2 and 1, this is 10, this is this 10. So I am writing this value here, and I will show you these values later on. And then on the slides, E and R is 2, so it is 3, 3 and J is 2, 3, 2, E32, E32, this is 3 and this is 2, so I have to keep 3, 2, 0.5, 0.05. So I am writing this value here, and I will show you this value later on. Okay, and then I have to see Wij, which is 22, W22. So this is my W, and this is 2, and this is 2, and this is the value 0.25. So 0.25. So now you have to sum up these values. 0.25. Already two values and plus 25. Plus 25. So 15 and 25, 30, 40. So 0.40 is the value of t, 0.40. 0.40 is the value of t. Now check. T less than E22, check this value. T less than E22. This is E, 2 and 2. 2 is infinity. 2 is infinity. So if 2 is infinity, t less than E22, value of t is 0.40. 0.40 less than infinity, yes, true. Put the value of 0.40 into E22. So this is E22. So remove this infinity and put the value of 0.40. 0.40. Also verify this value. This is 2, 2. So 2 and 2. This is the value. These values can update with the iteration of this for loop in the algorithm. And here in this slide, maybe some values will be updated. Let's see what will happen. So, and then according to this slide, according to the algorithm, what is the value of R2? So you have to write 2 in where? Root 2, 2. What is my root? So this is my root. And I have to write 2 into 2. This is 2 and this is 2. So I have to write 2 here. Okay. Loop is ended. I have to go again to the external loop, and now the value of I will be changed. And now the value of I will be changed. What would be the value now? Now the value, this loop is ended. It only runs. So now it is 3. And now the value of this L is 1, 1 minus 1 cancelled. So value of I is 3 now. J, the value of J is again, the value of J is also, value of J is 3. This E33, you have to put 3 infinity. Okay. Here, this is 3 and this is 3. You have to put infinity here. Okay, that's fine. And after that, you have to update the value of So in W matrix. So W33 is the place here in this empty cell. What would be the value here? 3 2. So wait, 3 2, 3 and this 2. So this one. So this value 0.05 plus P3 or Q3. So P3 Q3 is these values, and it is 0.10. 0.10 plus this value point plus this value 0.05. 0.10 plus this value 0.05, it is 0.15. So you have to keep 0.15 at 3 3. This is in W matrix. So this is W. So 3 and 3. So you have to 0.15. One more check. Yes. Okay. Now this is okay. And now the next loop from R is equal to I, which is 3, to J, which is 3 again. So this loop will execute again for one time only. And then you have to compute the value of T. Okay. Compute the value of T. And now from R is 3 and to 3, we have to compute the value like this. 3 to 3. And then, okay, check this value. 3 2, E32. So now I am removing this one because I have to update this value. So E32. So I'm not now showing you anything. I'm writing these values here. E32. What is E32? This one on the slide 3, E32. E32 is 0.05. So I'm writing 0.05 E32 plus E and um, 32 and E43, 43, E43, 4 and 3. That is again 0.05. And then weight 33, weight 33. So I have to look here at weight 33. So weight 33 is 0.15. So plus 0.15. So what would be the value here? 0.25 maybe. T is 0.25. Okay. So 0.25. So T is 0.25 less than, check nest, 0.25 less than E33. 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 What is the value at E33? E33. E33 has infinity. Okay. So it is less. So condition is true. When it is less, update the value at E33. So what is the value of T? 0.25. 3 and that's 3. 3 3. Now verify it here. 3 and 3. Verify it on the slide. Yes, it is. And then keep R here. Root 3 3. Value of R is 3. And you can, this one was the previous one, you can keep this one 3 3, this one. So you have to store this value at root. So you can store the value here. And maybe here again you don't have to need this part, and you will have your values in the upper portion. So you don't have to, in this way your diagram will be like this. And similarly, E, for E you don't have to need this part. and sorry, 1, 2, 3, 4, 5, and 6. And this way, in this way, you can go on and go on. I hope that now you have understand. But keep this thing in mind that these values are not final values. During iteration, these values can be updated when the value of t would be smaller than these values. Then you have to update these values, and in this way you can go on. Now I am moving. I can turn off the. For example, I was here at 2 5 and the loop was ended for 3. I try to run uh, without writing anything. So now the value of I would be 4, and 1 minus, so the value of I would be 4, and the value of j would also be 4. Put 4 for infinity here. The value 4 4 4 and 4, this would be infinity before any value here. And here weight 4 4, which would be 4, and this one, which would be this value. Actually this one is already done, so this one. So weight 4 and 3, weight 4 and 3, 4 and 3, 4 and 3. You will take this value 0.05 and P4 Q4, this one 0.15 and 0.05, 0.20. So you will keep this value at 4 4. This one, this 20 is now verified. And then you can run this algorithm again. So now it is 4, it will execute one time E43, then 5 4. 4 3 is what? 4 and then 3. This is 0.5, and then 5 4, 5 4, this is 0.05, and then weight 4 4, 4 and 4, which is 20. 20 plus 10, 0.30, which is 0.30, that is t. Third, 0.30 less than E44. E44 is E44. It would be infinity before, or this infinity. So it is less than, you have to update 0.30, the value of t here. And in this way you can go on. And then you will have your value, the value when you will get at this point, that would be the optimal value. Optimal value, keep this thing in your mind. That would be the value of the optimal BST, and that is 2.5. And here we have seen already that the value of this tree is 0.25. We said this thing early, and now we are just verifying. So that you have got here 0.25. And this one is only giving you the idea that now the probability is 1. Okay, it's probability because it is optimal. The probability value is normally remains between 0 to 1. So that is also an indicator that now the weight of this BST is 1, and it is the optimal one. All the other probabilities are something, the lesser, the subtrees with lesser. These are the subproblems, you can say. And these subproblems are giving their values finally here at this point with probability 1. You will get 1 here actually. And this is something, the extra table now containing the roots of the trees that you have. Now, this is also showing that 2 would be the root, 2, 1, 0, and so on. And in this way, you can go on. And by using this root, you can display the structure of the BST, which you will see here in the next in these next slides. So okay, so I will update the quiz on the Google class. I will create a Google class, and I will send you the link through which you can register yourself on that Google Class, and then I will put the quiz number one, or the first quiz on that Google Class, that you have to submit within the deadline, which I will mention there. And now these are the assignment portion. It is from the textbook. So here, write pseudocode for the procedure, construct optimal BST. So you have to construct optimal BST, which, given the table root, outputs the structure of optimal BST. So your program should have to output the structure of the BST like this one in these sentences. And if your roots are stored in R, you can simply display K2 is the root, K2 is K1 is the left child of K2 or anything. For the example, figure 5.10, you can also consider that figure. So this is basically, you have to augment this program. You have to modify this program, and so that it will give you the output like this. And then similarly, some other assignments from the textbook that you have to do, and that these assignments you again has to submit through Google Class. And this is the end. Thank you very much. I don't know, maybe you enjoyed the lecture or not, I don't know, due to these changing of boards again and again. uh, but I have these resources, so I don't know. So please give your feedback in the group, either this method is okay or not. Thank you very much. See you next time. Goodbye.